So my name is Laura Bégon-Lours. I work as an assistant professor in ETHZ Zurich in the Department of Electrical Engineering. And I'm the group leader of the Neuromorphic Electronics with Oxide group. And our role in SwissChip is to contribute to the work packages on devices and sensors. In fact, I'm a material scientist, and what I develop is novel material and novel processes to actually integrate functional materials into the back-end offline or CMOS devices in order to bring new functionality to these integrated circuits. What we want to build actually is devices that mimic the biological function that we have in the brain. This is what we call neuromorphic devices. So this is actually a very broad question. The really big challenge that we want to address is the cost of the computation of AI models on conventional architectures. And part of this cost is related to the data transfer between memory and processing. And what we know is that, in fact, AI models could be very well run on new hardware, new architectures, where this memory and the processing are collocated, exactly in the same way that they are collocated in our brain. In our brain, what we have is neurons that compute information, and these neurons that are separated or connected by synapses. What we want to look for, or what we want to develop, are methods to implement the synaptic functionality with electronic devices. And this is really what we are developing in the lab. We want to develop these solid-state synapses with, for example, functional oxides, semiconducting oxides, ferroelectric oxides. So this year was very interesting. It was a lot of processing work, so we were really in the clean room developing new processes, developing new materials. And what we achieved is really to scale down the lateral dimensions of our devices. Before, we were talking of devices that were maybe 10 micrometer large, and now we could really scale the footprint to go to devices that are less than 1 micrometer square. And this was difficult because we had to really change the lithography process and the fabrication process and really start from scratch. So the real achievement, besides the lateral scaling of these devices, was that we could increase the on-off ratio, so increase the dynamic range of our devices. We could also reduce the programming speed, and we achieved to program our devices with only 1 nanosecond, which is very fast and shows that our devices could be useful also for high-performance computing. So I think there are two ways to answer this question. One way to answer this question is really to talk about the high-level application of the technology that we are developing. We are interested in its application for neuromorphic computing, which is maybe a niche application and which is really at the research stage. But in fact, if you look at these devices, if you look at the material that we are developing, this material is already widely adopted by industry. For example, global foundries already commercialize it to basically offer non-volatile memories that are as fast as volatile memories. So it really opens a new category, a new class of memories that could be used also for digital computing. And the second answer to this question is what we provide here as an academic institution. And I think we really contribute to training people, to give people the know-how and the knowledge to really develop this new material, these new memories. We train people in the clean room. We are extremely active, for example, to share our processes and our programs, our script on open source platforms like GitHub. We are really willing to contribute to this ecosystem and to train the people which will basically shape this ecosystem now and in the future.